Okay, welcome to another Orbiter 2010 video, and in this video I have Dimitri here with me again. Dimitri was a huge help to us all, helped us learn how to use IMFD, and I for one am very thankful for that because I've been able to make several flights since recording those videos with him, so hopefully you all will appreciate him coming back again and helping us one more time. In this flight we're going to do something that's a little bit more sophisticated. We're going to go from Earth's moon directly over to Venus. And this isn't going to be one of those missions where you kind of drop down to Earth and do kind of a slingshot effect. We're just going to go directly over to Venus. But it does introduce some interesting problems that perhaps we can overcome. So, Dimitri, what do we need to do? How do we get started?
Okay, hi everyone. Well, as usual, we open IMFD on both sides. And this is, like you said, a direct flight from the moon to another planet. It could be Venus, Mars, whatever. And this is something that can be set up also with TransX, but it's a lot more difficult to set it up. And it requires some juggling between two instances of TransX. For this type of flight, going directly from a moon to another planet, IMFD is perfect to help you with the setup and the execution of the flight. In this case, where we're going from Earth's moon to another planet, we're actually wasting a little bit of fuel compared to dropping to a low Earth periapsis and making a second burn there. But in that case, IMFD cannot help that much. We need TransX for that kind of setup. So it's always good to know which tool to use for which situation, which is the best tool to use for which situation. And for a direct flight, IMFD, from a moon to another planet, IMFD is the best tool in our arson, let's say, for the interplanetary flights. Like I said, in this case, we're wasting a little bit of fuel, but for example, if we were on Europa and we wanted to get back to Earth, then the direct flight is the way to get back to Earth using minimum fuel. You wouldn't want there to drop to a low Earth perijovion, let's say.
Could you maybe explain a little bit of the physics perhaps behind what when you're saying we're going to waste a little bit of fuel? That's because if we drop to Earth, we're going to have a velocity of about 11 kilometers per second by the time we get back there.
So exactly. We are going to use about 0.85 kilometers per second to drop back to Earth. But when we arrive at Earth periapsis, we're going to have about 11 kilometers per second velocity. So since a trip to Mars takes 11.4, 11.5 kilometers per second to actually get to Mars as the injection velocity, not the delta V, we're going to have a difference of 400 meters per second when you reach Earth periapsis. So you end up using 1.3, 1.4 kilometers per second if we include the corrections, and you get to Mars. Going directly from the moon to Mars takes about 1.7 kilometers per second, so it's a little bit more expensive, but it's easier to set up, so there is a trade-off over there.
Yeah, and that's important, I think, for a lot of people who might just be, getting their feet wet with the idea of going from the Earth's moon out to another planet. The first flight or the first example should be a little bit easier, and then they can learn more sophisticated methods later on.
Yeah. And like I said, if we were on Europa and we're getting back to Earth, then dropping to a low periapsis around Jupiter would actually cost a lot more fuel than to leave directly from Europa, because Jupiter is so huge and Europa is, compared to Jupiter, very, very small and also very close to Jupiter. So in that case, you're wasting fuel if you leave Europa to drop to a low periapsis around Jupiter and then make a second burn. In that case, you're far better off to leave directly from Europa and get back to Earth. So that's where you would absolutely need this kind of setup. So we're going to show it but because that flight takes a long time, we're going to show it in a moon to a Venus flight, which is relatively shorter.
Just a quick question that came to my mind while you were talking about the Europa to Earth. Is there any good way to know, like a rule of thumb, like when the direct flight is better and when it's not?
Well,
Or does that just
for
require a
Jupiter,
bunch of calculations?
not if we're going to compare between living directly from the moon, from a moon, or dropping to a low periapsis around its parent planet and then making a second burn, as far as Jupiter is concerned and all of its moons, you're always better off living directly from the moon, from the moon's orbit, from the moon's surface, getting into orbit, and then ejecting from the whole system directly from the moon. You don't want to drop to a low Earth, to a low Jupiter periapsis. Same goes for Saturn, except perhaps one moon. I think I can't be really sure, but usually it does take a little bit of calculation, because even for Jupiter, for some flights back to Earth, perhaps a very fast flight where you want to make a sling or something like that, in that case you may want to do the calculation. I actually have a spreadsheet where I have all those calculations set up, so in another flight we can go through those calculations and actually show how to choose between which method to use. But in general, when leaving from a moon of Jupiter to go to another planet, it's always best to leave directly. When leaving from Earth's moon to go to another planet, it is always best to drop to Earth, to low Earth periapsis, and then make a second burn.
Yeah.
And for Saturn, it's pretty much the same as Jupiter, as the rule for Jupiter. For Mars, where the moons are tiny, you're also, in most cases, pretty much better to live directly, because you don't go into orbit around the moon. In that case, it's like you're landed on a spaceship, you undock, and you live directly.
Yeah.
From Phobos and Deimos. Now for the other outer planets, I really have to check. I don't make the flights to those planets very regularly to remember it.
Yeah. Well, that gives everybody a great background on the pros and cons of leaving directly from the moon and going to the planet, or dropping back to the parent planet first. So
and in terms of realism, if you think about it, it wouldn't make much sense to be on Europa and drop to a low orbit around Jupiter because of the radiation and all that stuff.
Yeah.
But of course, that's not simulated in orbiter.
Yeah, the different vessels don't have any radiation detection, or they don't get affected from radiation. All right, so let's go ahead and jump in here on the one of the MFDs. Which program do we need to bring up on IMFD?
First, we need to set up a course to Venus. So I think you already know how to do that.
I don't guarantee that.
A course? Okay, a course to Venus. From what I said, okay, that's good. The course program. And target intercepts.
Okay. And then we're going to target Venus?
Yep. Now, we're looking at the IV, at the OV vector. Now, of course, it depends on your planning on what you want to do on your arrival. If you're setting up a whole journey, you don't just set up to leave the planet and arrive there no matter what. You also want to know what you're going to do when you arrive. Because if you arrive with a very, very high encounter velocity, you won't be able to stop. So you need to take that fuel into account. But in this case, we're just going to make a Hohmann transfer. We're going to try and set up something like that and get to Venus.
Okay.
So the best thing to do would be to lock the time of flight and start changing the dates until you get a minimum OV solution.
Okay, so we'll come down here to TOF, unlock, toggle that, and then we want to start with the...
Whatever you change, it doesn't matter, because both get, once you lock the time of flight, as many days as you add on one side will get added on the other.
That's
But
right.
you want to go to 10x or 100x until you get a minimum solution.
And I guess adding in time or taking away doesn't matter because we'll use the scenario editor either way
You
to...
can you cannot take away time when you reach 0. When you reach this date, you cannot go back. Compared to TransX, where you get the date you want. But in IMFD, if you reach, you cannot go back from today's date.
Okay, that's good to know. I didn't know that. So we're going around here and we're looking for a delta V that's, I actually don't know what the, like a low delta V cost would be.
I think you passed a nice plan. Let's go a little bit back.
Yeah, this here looks like a Hammond
There.
transfer.
Yeah, and also you can see the OV, it's almost 2765.
Yeah, let me just do an adjustment to find that lowest point. And looks like it's about there.
Okay, and now you can unlock the top and start making adjustments.
Okay, now when we unlock the time of flight, do we want to start with the, or does it matter which date we start with?
It doesn't really matter. For some planets, it's going to get better. For others, it's going to get worse. It doesn't really matter. You go either in one direction or the other until you get a minimum, and then you go and change the other variable.
So the idea here, it doesn't matter which one we start with. We just want to adjust the date forward and backward, watch the OV. Then when it gets to its lowest point, we go to the other one, just like we did with Mars, I believe.
Exactly.
Okay, so here we're adjusting the arrival date, and that's actually starting to get a little bit worse.
Now, don't worry too much about getting the absolute minimum, because this time we're not living from Earth, where we have... so let me explain that. When you are on Earth, all you have to wait for is one spin for the planet to rotate once, and you get 2 chances to launch in the correct orbit.
Mm-hmm.
Now we're starting for the moon, so it takes a whole month to go around the Earth and to get into the correct orbit. So right now, let's just find a date where we have a relatively small OV vector, which is basically the outward velocity, the outward delta V that we're going to need. And then I will show you how to proceed from there. But don't worry about getting the absolute minimum.
Okay.
If it, well,
it's still going down.
It keeps dropping a lot. Yeah.
About right.
That's some.
And are we looking at like the moon is at an inclination from the Earth? Does that play into this at all, where we have to get our inclination down?
The way that we are going to leave the moon will also have a little bit of plane change in it, but you're going to be able to see that when we open up when we connect the other interplanetary IMFD. But for now, let's try and get it somewhere close to the minimum, and when you're satisfied, we can connect the other interplanetary IMFD.
Yeah, to me this looks about as low as that OV is going to get, and I also happen to notice that the EIN is low. I don't know that that matters at this point, but...
Okay, yeah. It means that it doesn't use a lot of plane change in this kind of flight.
Okay. So I opened the...
so on one side, we have a course for Venus. So open up, yeah. We share from the left.
Share from the left.
This time you use the slingshot program. We're not actually making a slingshot, but this is the program that we need to use. Now, this is the tricky part. In interplanetary IMFD, as you may have noticed up to this point, it's all about setting up the correct source and the reference in whatever program you're using.
Okay.
In this case, our source planet, in a sense, the planet that we're going to live from, which is it? I'm talking about the planet, not the moon.
The source planet is Earth.
Okay, so use that as your source.
Be reference Earth?
Yeah. Sorry, not reference Earth. We're also going to need that, but set the reference Earth, and now, no, that's correct. And now the source of the trajectory that we want to find to live is going to be... No, sorry. The reference was the Earth, that's correct. Now the source, from what you can see in there, in the middle that's Earth. Okay.
Mm-hmm.
The green orbit around the Earth, what's that right now?
It's the moon's orbit.
But
It's ours. It's our vessel.
Exactly, it's our vessel, but we want the moon, so we need to change the source
to the
and
moon.
set it to the moon. Mm-hmm.
Okay, so okay, that makes sense, sort of.
Okay.
So now we're saying in interplanetary MFD speak, we're saying that we want to move a vessel called the moon to Venus.
Exactly, and then it's going to give us a launch heading for our spacecraft to go into the correct orbit around the moon, and then it's going to give us from the orbit eject program the correct, let's say, burn parameters in order to eject the moon and go directly to the planet that we want.
Okay.
Okay, so we have a date. The date of departure is pretty far away from today, correct?
Yeah.
So we may want to use the scenario editor. If it was an Earth flight, you would set it up one day before. This time it's a moon flight. The moon takes about a month to go around Earth, so set up the date 1 month before the departure date.
Okay, so we're going to have 579 or 57291.
No, that's the arrival date. You
Okay.
want the departure date.
Okay.
57161, so make it 57131.
And then the decimals don't really matter. Okay.
Yeah, that's...
All right, so now our MJD is set appropriately, and should we... In Transx, when you make big adjustments to the date, you always have to go back to your plan and make adjustments. Do you need to worry about that in IMFD?
Well, we're going to have to worry about setting up actually matching the date on the left, the MJD of departure, with the MJD of departure here. Now, this is really important to show that there is a bug in interplanetary IMFD, so even if you do change the date, it will not actually change in the calculation. So what you need to change is always the time to ejection, this number, the number of seconds until the burn.
Okay.
And you can match it up to the TEJ over here.
So by default, or for starters, we can just type in the 2.591 M.
Yeah.
All right, let's do that.
Okay, so you can see the OV vector on the right side.
Mm-hmm.
If you had a spacecraft named the Moon and you wanted to get on the trajectory on the left side, on the heliocentric trajectory that will get you to Venus, then that's how much delta V that you would need in order to push it out of its orbit.
Okay.
Let's find a way to minimize that. Okay, first try, and obviously you can see from the shape of the trajectory over here, you can also zoom out a little bit if you want.
I am not seeing your mouse movement. Are you pointing to the left, MFD?
I moved it out of the screen completely, so you can zoom out a little bit on the right side.
Okay.
Now you can see that it's not perfectly aligned. The burn, let's say, to leave the moon is a little bit misshaped. It's burning a lot to the outside.
Yeah. I think what you mean, if I'm understanding, this is where it's saying the burn will take place, will be here, and we want it to be here.
And also, somewhere closer to that, you will see by changing the time to eject. Of course, you will have to go to 100x because you can only change the number of seconds. Never change the date on this on the interplanetary slingshot program. Go to 100x, start changing the time to eject until you get a minimum escape vector, and you will also watch the shape of the orbit get closer to what you want.
Okay, and do we want to go backwards with the date or forward, or do we not know?
I think we want to go backwards, but if you don't know, try it one side and then you can try the other. What you're looking up is the escape vector on the bottom of the IMFD that says OV1873.
Okay, and we're
And you
getting...
want to minimize that.
Let's go to 100x. Okay, going backwards is actually bringing it down. Well, do we just want to kind of stop here at that point because it's pointing straight at that periapsis point?
Well, it should be also very close to the minimum at that point.
Let me zoom in one level.
Now it's going up.
So we want to go back to... Yeah, right there at that point
Right
is...
there.
Yeah.
So it says PET, and past the PET, about 2000 seconds past the periapsis. Of course, we're talking about the orbit of the moon around the Earth, okay? It's 27 days, 27.32 days to make a complete circle. 1000 seconds, 2000 seconds, 10,000 seconds after the periapsis, it doesn't really matter. It doesn't affect the trajectory that much. So there we have a time to leave the moon and get into the trajectory that we want. But we also have to match the time to eject on the left side. Because on the left side we're saying that we are going to live on 2.591 million seconds, but on the right side we're saying that we are going to live at 2.475 million seconds. So these two have to match.
So on the left side we put in the new TEJ.
Mm-hmm.
Okay.
And this will change the OV. So you will notice it also change. You should
yeah.
also M.
Yep. 2.4.
1819.
Yeah, I actually didn't write down what it was before. It was, I think it was 1813 before.
Yeah, it's slightly higher, but it's not that big a deal. You can also keep making adjustments on the right side to see if you can get another minimum. But because we are, you do remember that we are 1 month away right now from the actual date that we want to leave.
Right.
So after you make this first adjustment, you can time warp forward until you get, let's say, 90 degrees before the burn, 1 week or 2 or 3 days before the burn, and work again with the variables. So we are right there right now, and we want to go one whole orbit around until we get to the blue trajectory. But don't get exactly to the blue trajectory, go about a day or two before.
Yeah, I'll just use the scenario editor to bump the date forward and be a lot faster. So that's 90 degrees or about 90 degrees there.
No, go closer, go about 45 or even less, about the day before.
That's probably
that's good, okay.
Okay, and now we want to...
It did go up from 1819 to 1821. Now you want to match the time to eject again.
Okay.
We are going to have to go back and forth between these two variables for a while until we get a minimum escape vector on the right side. Okay.
Now do we want to adjust the time here again?
Yeah. Go to 10, yeah, to 100.
Looks like 21's the lowest.
Mm-hmm.
Yeah. Yeah, 21's the lowest. So now we want to set the TEJ on the other side.
Yeah. When you have this, if you set 138.5 and you press enter right now, it's going to start counting from 138.4. You see?
Yeah.
So this is a little bit, set it 138.55.
Okay.
And it's going to be much closer to the actual the value of the right side. So there isn't that much to do right now. Let's get a little bit closer. And when we are approximately 1 hour before the time to eject, we're going to launch and get into the correct orbit around the moon. Now, is this part sensible so far?
Yeah, I think I would. I mean, I'd have to go through and I'll go back and watch the video a couple times to have it memorized. But I'm able to follow. I'm able to follow what's going on. A lot of the the previous examples, in the first getting started with IMFD, that helped a lot because I now have a better understanding of what I'm looking at with the different IMFDs. I have a better sense of how to navigate around them, so it's not nearly as difficult to follow along now.
Yeah, this is a new part of IMFT, and as usual with a new part, there's always some difficulty and when you don't understand where you're setting up. But if we do one or two examples, it's going to be much easier.
Yes, we'll bring the TJ down to about 3600.
Yeah, go to about 5000, so you may have to make a small adjustment because I can see on the left side, you see the numbers not matching.
Yeah.
But the difference is too small to even bother adjusting it. You don't have to adjust 10 seconds difference in a flight that takes, I don't know, 170 days.
Now at this point, it probably wouldn't do us any good to try to refine the OV any farther, I don't think.
You can try, but only by 1000 seconds or so.
Okay, so do we want 10x at this point because we're getting...
Yeah.
Okay. And going backwards, let's go to 100, I guess, even. And I reset
you
it.
Can go, as you can see, you can go by before the time of what's right now.
Okay, let's try that again. I didn't realize I was adjusting the time so much, but yeah, it doesn't look like it's doing any good to adjust the time, so.
Yeah, well, it's a little bit counterintuitive because at 10x you're not changing 10 seconds with each click, you're changing 1 minute with each click. And at 100x we're changing 1 hour with each click. This happens only on when you're changing the number of seconds. When you're changing the number of days, it goes normally. 0.1, actually it goes 0.1 days, 1 day, and 10 days. The 3 different settings.
I'm just setting the TEJ on the left here to match more closely.
Okay, and I think we are ready to set up the orbit eject program. Here I usually wait until I'm 1 hour before launch. Why is that? Because it will take a little bit of time to launch the spacecraft and get into the parking orbit, and then you may have to coast all the way across to the other side of the moon.
Yeah.
To make the burn. Sometimes the coast may be a little right next to your base, or sometimes you might be slightly past the burn, and you may have to coast almost 360 degrees to go around and make the burn. So as an average value, somewhere around 1 hour is okay to cover for this difference from the time that you launch and up to the time when you are going to make the burn.
Yeah, that makes sense. If you have to go all the way around, you need that additional time, especially on the moon, because it takes longer to orbit than it does even on Earth. All right, well, actually, let's set that up in part 2 of this video because we're already at 30 minutes on this part. So we'll save setting up the eject or the ride to orbit for the next video.
Okay.
All right, if you like this part of the video, hit the like button down below, and please leave a comment thanking Dimitri for helping us with all this, and I'll put a link to his YouTube channel down in the description. Be sure to check that out, and I will see you in the next part.